Hello, my name is Boris Tankhilevich, and I represent Magtera. This is a small startup located in California, and we are inventing terahertz magnon laser. This is a new kind of device that allows to unlock terahertz spectrum, bridge the so-called terahertz gap by providing source of terahertz radiation, which is tunable, operational at room temperature, can be tuned by using voltage, and can be produced by using the conventional method of MRM memory. This presentation will be how to use this device to provide different means, new means for the recording and reading data. I would like to discuss this with you today. So basically, we are talking about writing and reading data with negligible energy dissipation in the data storage medium by using terahertz magnon laser. Data centers represent the information backbone of an increasingly digitalized world. As you know, demand for these services has been rising rapidly, and data-intensive technologies such as artificial intelligence, smart and connected energy systems, distributed manufacturing systems, autonomous vehicles promise to decrease demand even further. It's also a very energy-intensive thing. This center estimated to account for around 1% of worldwide electricity use. These trends have applications for global energy demands and must be analyzed rigorously. Over the past decade, the energy use was tripled, and in the future, it will quadruple in the next decade. So this is a problem with the data centers. They consume a lot of energy, and they also dissipate a lot of energy. Some of these centers had to be placed even underwater to deal with those problems. So we would like to address this problem by introducing completely different method of reading and writing data and using different kind of memory. So all current method of writing and reading data involve usage of electrical current. So our approach is different. We don't introduce current into the system. We manipulate spin current within the system. That is why we will use much less energy to affect memory writing and reading. Basic memory cell we would like to introduce is a spin wolf comprising two magnetic metals, for instance, nickel 80, cobalt 20. This is alloy. This is the same alloy, separated by ruthenium spacer, which is a normal metal. These two layers of ferromagnetic metal interact through this spacer by so-called RKKY interaction, which provides connection between exchange field within these two layers. And the interesting side effect of this interaction, that it is oscillating interaction, the sign of this interaction could be ferromagnetic or antiferromagnetic, as you see here, depending on the thickness of the spacer. So for instance, for first one thickness of the spacer, as you see, these layers are parallel, and the overall momentum of the system will be zero if we choose each of this moment equal to half of this reference layer cobalt. In the other configuration, in the other thickness of this ruthenium, these layers will be anti-parallel, F2 layer, F1 layer. In this case, they will compensate each other. is the overall moment of the wall will be equal to the moment of the cobalt. So that means that we can encode information either bit 1 or bit 0, depending whether these layers are parallel or anti-parallel. However, in order to use this memory, we need to change the thickness of this layer, which looks impossible because it is a physical thickness. However, there is a way to do it. It can be done by controlling the oscillatory interlay exchange interaction with terahertz radiation. This was published recently in 2017 in Physical Review Letters. So what is the basic idea? The idea is that by introducing terahertz radiation into the system, we manipulate the scattering properties of the current, spin current, between layer F1 and F2. And manipulating this time of flight properties, we effectively change the thickness of this layer. And this really works because based on their calculations, this is a theoretical paper, there was no experiment so far. We can see that if we encode sign of the RKKY interaction in the blue as a ferromagnetic and red as antiferromagnetic, at terahertz frequencies from 10 to 200, we can observe these effects. Our laser can provide frequencies from 3 basically to 30 terahertz. So we can operate in this region. So as you can see, at certain terahertz frequencies that our laser will generate, by changing the bias voltage, we can go from this area to this area, and indeed will change the sign of interaction. So by modulating this bias voltage by information that we want to encode, we can go to this layer and back and provide a writing of the information into this kind of memory. Wavelengths of the terahertz photons between 10 and 30 microns. The size of spin waves is about hundreds of nanometers. So these photons will have no difficulty to penetrate the spin wave and to enable the required change of the sign of RKKY interaction. So this procedure can be done by using terahertz magnon laser invented by Magtera. Let us talk about this laser in some details. This is the photographic picture of this laser. You can see it is very small, and it has very important properties. It is broadly tunable even voltage, covering the whole terahertz gap. It has a very narrow linewidth if we reach the magnon lasing point, can easily generate milliwatt power, and can be scaled up. And it is very compact, cheap scale device. Operation room temperature, can be fabricated using low cost wafer scale production, similar to MRAM. So let's talk about a little bit about physics of this laser. This is a conventional optical laser. It has to have 3 layers. And when you pump electron to this layer, it has very fast transition to this intermediate layer. And there it is waiting for the photon to pass by. This photon will affect change in transition of this electron from level 2 to level 1 and provide additional photon. That's how you have multiplication of the amplification of the photons resulting in the lasing process. Our laser is based on also lasing properties, but magnons as opposed to photons. The main idea is to use either ferromagnetic semiconductor, as shown here, or half metal, as be shown later, and to eject electron with spin down in a subband with spin down. In normal situation, there's no electrons here. So this electron, in order to lower its energy, as every system does, has to flip its spin, because this is a subband with spin up. It can be done by emitting magnon. In this position, in this state, electron, instead of a reabsorption magnon, very rapidly will emit optical phonon, here in the case of ferromagnetic semiconductors, or will scatter on other electron on the Fermi level in the case of half metal, as we talk later. And we will get out from the picture. So this process will result in emitting of magnon. This magnon has interesting properties. It has terahertz energy, and it is actually a lasing process, as you can see, because we have this analogy, three-level process again. We pump electron into this level, we have magnon emission, then electron, by emitting optical phonon, get out from the picture, and we have again three-level system, but for magnons. For the half metal, as you see, situation is similar, but instead of emitting optical phonon, as I told, electron will dissipate on the Fermi level with other electrons at this level. You also very rapidly will get out from the picture. So the basic transport equation for these processes are, so we provide electron, and this electron will produce magnon, and in this diagram you can see this is a diagram for magnons. Magnons are being born by spin electrons, by clipping their spins, and this non-equilibrium electron will relax on equilibrium electrons in this four exchange process. To make it more clear, we have this diagram. So we have non-equilibrium magnon will be relaxing on the equilibrium magnons, resulting in two equilibrium magnons in an exchange process. And finally, these two non-equilibrium magnons can merge and produce terahertz radiation. These magnons occupy this part of the spectrum. This is the Bose state spectrum for magnons that exist in any magnetic system, and this shows the equilibrium magnons, non-equilibrium magnons that we generate in this narrow region. With increase of pumping, this region will be shifting to the left, and the intensity of this magnon spectrum will increase accordingly. As a result, we'll have magnon lasing process. We'll have steady state in this system because if we pour non-equilibrium electrons into the system, and this hole shows the exchange scattering of the magnons, this shows that we can have some steady level at any pumping level. However, we also, as was explained, have small leakage of terahertz photons. But because this interaction is relativistic, and this is exchange interaction, this interaction is much more intense than this one. It means that this hole is much less than this hole, and we have a quasi-steady level of the non-equilibrium magnons in the system. The lasing frequency is described by this equation where D is the magnon stiffness, P0 is related to the gap in this to this gap, and the P0 describes the P, it is the momentum of the injected electrons. In order to reach the lasing level of magnons, it is sufficient to apply not very high current density like 10⁻⁶ ampere per square centimeters, which is quite feasible for nowadays. So this is basic design of terahertz magnon laser of the strong junction. Strong junction is necessary in order to enable spin injection. This is the real device. As you see, it can be fabricated by using current MBA technology or spatial technology. This shows how we do tuning. Basically, tuning is affected due to this dependence of the magnon phasing frequency of the energy of electrons. And by increasing energy of electron, we shift frequency to the low numbers of the frequency, and we can cover the whole spectrum. So the same approach as was discussed was applied to the writing magnetic data to the memory. We can also use it for reading of data recorded in the magnetic wave separated by RKKY spacer, with negligible energy dissipation again in the wave itself. It can be done by placing the memory cell close to terahertz laser and providing some bridge between the magnon laser and the memory cell, so that this bridge will be magnetized to the higher or to the lower level, depending on the encoded bit of information. And if we send magnon, generated high-frequency magnon into this bridge, the energy of the magnons will depend on this momentum of the bridge due to exchange to the gap in the magnon spectrum. So this effect was actually patented in the patent also belonging to Magtera, tunable generation of terahertz radiation depending on the external magnetic field. So because in the state 1 we have stronger magnetic field, ferrostate, than in state 0, we have different frequency of the terahertz radiation, and we can demodulate this radiation by using Schottky diode, and we can extract the recorded data. So what we are here having is nothing less than a really revolution in the magnetic memory. It can be compared to transistor revolution, that when we replaced vacuum tubes with the transistor, we basically achieved about 10 million times energy effectiveness. Basically, the same kind of revolution can be happen in this method of writing and reading information using terahertz signal generated by magnon laser and using the RKKY based memory. The basically effect is 10 million times lower power in both situations. So basically, we'll have a real problem, if not today, but very soon, because the amount of data is growing exponentially, amount of video, data, any kind of data. In order to provide necessary means to be consistent with this demand, the ways to use memory, to record information, to read information, and to what kind of memory can be used should be changed. Magtera call for action because we actually have solution to this problem, and Magtera is actively seeking investors and our partners to develop this revolutionary and proprietary technology. So we are interested. This is my contact information. This is my cell number, 510-305-5320. Those are my email numbers, email addresses, and that's what my presentation. I want to thank you for your attention, and I hope that we can have some kind of a communication further to enable this kind of technology.